Thank you. Today I'm going to talk about what makes a species a successful invader. And I'll try to convince you that life history is important to understand why some species are so successful invaders. Like you see here, the black rat or the house sparrow or the mosquito, the tiger mosquito. And I try to convince you that to understand why these species are so successful, you should look at life history. But that the reasons that make them successful invaders are different from those generally assumed in the literature. Oops. So life history explains how organisms allocate time and energy into growth, reproduction, and survival to maximize fitness. So in so doing, it explains why some organisms are small or large, why they have many offspring or few offsprings, or why they live long lives or short lives. And all these life history traits are important because they determine the way the population increases in number and fluctuates over time. So life history has long been suggested to be an important way organisms deal with environmental changes. And perhaps the most popular theory, it's like cut a bit, the most popular theory is the population growth theory proposed by Richard Lewontin over 40 years ago. And essentially the theory proposes that the organisms that have life history that allow them to reproduce more would be better invaders because these species are capable to increase in number faster, so they are more capable to avoid the period at which the population is very small and therefore very susceptible to extinction by accident or by demographic stochasticity. And actually, this theory is well supported by demographic models. Like you see here, you can see here a very simple model where you have different age classes, and you have demographic parameters like survival and fecundity, and you make these demographic parameters to change at random. And then you can run simulations for different propagule size, that is for different number of individuals released, and then you compare species that have life histories that invest in reproduction compared with those that invest in survival, like for example. So if you run this kind of experiment, what you find is that the life history that allow a faster population increase are the ones that tend to be more successful invaders. However, when this theory is tested empirically, the things are not so clear. And here I show you a table with some of the studies that have been conducted in birds. These studies, essentially what they do is to use a number of life history surrogates of population growth rate and compare these life history traits with the outcome of introductions. These introductions are not experiments, are historical introductions where we have information about the success or failure. And as you can see, some of the studies support the population growth hypothesis, but some others do not, and even you have some studies that find the contrary that you would predict. So to try to understand what's going on here, we recently conducted a global analysis of avian introductions. We look for information of many different introductions, and then we also look for information on many different life history traits, and then we use a number of analytical techniques to try to uncover patterns. And what we found was that from all the life history traits that had been previously used to test the population growth hypothesis, only clutch size is correlated with establishment success. But contrary to the hypothesis, the effect is negative, not positive. So species that lay larger clutches are not better invaders, but worse invaders. And this result also is consistent when one introduces a propagule pressure in the model, when one controls for the fact that some introductions involve many individuals and some others very few. One problem when using clutch size to quantify population growth is that you can have a species that lay small clutches but have a high reproductive or a high population growth simply because it reproduces very frequently. So what we try to do is to use more direct measures of population growth by solving Cole's equation, which is the equation you can see over here. And this gives you a measure of the maximum potential for increase of the population. And when you use this direct measure, the results again are inconsistent with the population growth hypothesis that you can see here. So Rmax is not related with establishment success, and the same is true when one controls for propagal pressure. So how come a theory that it sounds, then it cannot be verified on empirical grounds? So I suggest that this is because of two flaws of the theory. The first flaw, it relates with routes toward extinction. When one population is introduced, it faces a number of novel environmental pressures, like a bird has to find food and novel food and has to avoid predators that the species doesn't know. And so an important route toward extinction in introduced species is the negative population growth, because the species is not well adapted to the new environment, and also because the species has no information about the enemies and resources in the environment. But even a species that has the appropriate adaptations to survive and reproduce in the new environment can still fail to become established because of bad luck, as I already told you. And this is because, as I told you, the invaders very often start with very low numbers. So this means that they are very susceptible, the population is very susceptible to extinction by demographic stochasticity. So the population growth hypothesis just focuses on this route toward extinction, but says nothing about this other that, as we will see in a minute, is very important. And of course, we know that demographic stochasticity is an important route toward extinction in introduced population. And for example, there is evidence that there is a correlation between the number of individuals that you release and the probability of establishment. So this is data for birds, and comparing the historical introductions that were successful and the ones that were unsuccessful. And as you can see, if you release between 2 and 20 individuals, the probability of failure is very high. But if you release more than 200 individuals, then the probability of success is much higher. However, it has been known for some time that the relationship between the number of individuals that you release and the probability of establishment is nonlinear, and achieve a threshold above which the release of new individuals has no effect on the probability of establishment. And this graph over here is just to show that this is not an outlier. And what this means is that, well, in the case of birds, this is an example of birds, and this threshold in birds is less than 300 individuals, which means that for many of the introductions we have in our files, probably demographic stochasticity is not playing a role in explaining the failure. And this is what this graph shows. This graph represents the effect of Rmax, the maximum population growth rate, on the probability of establishment for birds. And as you see here, if we use all the information of historical introductions, you see that there is no effect. The effect is close to zero, the effect of Rmax on the probability of establishment. But this effect increases when you restrict the analysis to introductions with a smaller propagal size. Like, for example, if you use only introductions with 5 individual release, you see that the effect of Rmax on the probability of establishment is almost significant. So what this trend suggests is that demographic stochasticity could be an important route toward extinction in introduced population, but only when the initial population is very small. So another flaw of the population growth hypothesis is that it doesn't take into account the fact that investing in reproduction also involves costs. And one important cost is in terms of survival, which determines this fast-slow continuum, where we have in one extreme the fast-lived species, that are species that invest in high reproductive rates at the cost of surviving poorly. And at the other extreme, we have slow-lived species, that are species that invest in survival but have low reproductive rates. And the existence of this trade-off has two major consequences. One consequence is that has been shown, and in fact is known from some time, is that although the fast-lived species tend to increase in number faster, they also tend to fluctuate more over time compared with the slow-lived species, which means that for a same population growth rate, the fast-lived species should be more likely to become extinct than the slow-lived species. So what this suggests is that the success of the fast-lived species compared with the slow-lived species will depend on whether or not the species is capable to maintain a rapid population growth in an environment to which is not well adapted. And this can happen, for example, if the adaptive peak in the region of origin and the adaptive peak in the region of introduction are very similar, or when the invader has broad environmental tolerances, so the adaptive peaks overlap between each other. But when the adaptive peaks are very different, then the most likely outcome is that the rate of population increase should decline, unless the species has adaptations that buffer the population against the new challenges that the species find in the environment. And theory suggests that the species that has a fast-lived strategy should be less likely to have this kind of buffer adaptations. And the reason is that for us low-lived species to invest in adaptations that allow the individuals to survive better has higher fitness benefits. So it's much more likely that this species evolve this kind of adaptations. In the invasion literature, there are two main buffer adaptations that have been suggested. One is body size, but actually, at least in vertebrates, there is no clear evidence that being larger provides you any kind of benefits in terms of invading new environments, but we have better evidence for the brain. And this is what's called the cognitive buffer hypothesis. And the idea here is that the species that have a large brain should be better able to survive in new environments because the brain would allow them to respond to many of the challenges like finding food or avoiding enemies by means of the construction of behavioral responses, like for example, through learning or through innovation. And in fact, animals are capable to resolve many of the problems they have by means of changes in behavior. And here I put a couple of examples to show how animals can solve important problems. So if you can run the video, please. So what you see here is a green-backed heron. This individual, what he's doing is dropping small pieces of bread in the water to try to attract fish, to then be more capable to trap the fish. So what it is doing is dropping the bread, and then you will see the bubbles of the fish that are attracted. And in a second, this guy is going to trap the fish, hopefully. This guy is a bit slow. This second example is
devised a way of eating a food that normally they can't manage.
Is a crow. And in some populations, they have devised a method to exploit a food that they normally cannot eat, the nuts. And the technique consists in dropping the nuts from some height, hoping that the nuts break when crashing on the ground.
Dropping a nut from a great height onto a hard road does sometimes crack it. But some nuts are particularly tough.
But the problem is that some of these nuts
So the crows have devised a better way.
solution, which consists in dropping the nuts in places where you have traffic.
Drop it among the traffic. The problem now is collecting the bits without getting run over. So some birds have refined their technique. They station themselves beside pedestrian crossings. Wait for the lights to stop the traffic. Then collect your cracked nut in safety.
So these kind of behavioral innovations are very common in many animals and allow them to find novel foods or water, or to avoid predators, or to adjust the behavior to the reproductive conditions of the place they are introduced. So they have long been suggested that they could be an important way animals deal with challenges. And actually we have evidence that in birds and also in mammals and reptiles, there is a relationship between the size of the brain and the potential, the invasion potential of the species, as you see here. This is for birds, and you see that the species that have larger brains also tend to have a higher invasion potential. And the next thing is that this relationship between the brain and the invasion potential doesn't seem to be direct, but seems to be caused by the behavioral flexibility of the species. So essentially what this path analysis shows is that having a large brain allows you to invent new behaviors or learn faster, and this is what helps you to survive in new environments. So to sum up, we have just seen that the population growth hypothesis can be true, but only under some situations, like when the population is very small, and when there is environmental matching between the place of introduction and the place of origin of the species, and also that it involves some cost. Investing in reproduction has also some cost, like higher stochastic fluctuations and the lack of buffer adaptations, like a large brain. So maybe are not the species that invest in reproduction the ones that are more successful invaders, but those that invest in future reproduction, like the ones that invest in survival. So to test this new hypothesis, we look at the relationship between the fast-slow continuum and the probability of success, or the invasion potential of the species. And the prediction would be that the species that are at the extreme, at the slow extreme of the fast-slow continuum, should be better invaders. But as you see here, there is nothing. So there is no relationship between the fast-slow continuum and the invasion potential of the species. So this can mean maybe that the advantage of investing in reproduction or survival maybe counterbalance each other. Maybe none of the theories is correct, or perhaps maybe we have forgot some important elements in the theory. And I think we have actually forgot some important mechanisms that should also be taken into account. So in a strategy of future returns, you can have benefits in terms of buffer adaptations and stochastic fluctuations, but this strategy is also based on distributing the reproductive effort in many different events. And this has two main consequences. The first is that reduces the cost of a reproductive failure. for a species that is invading a new environment, it's quite likely that there is a reproductive failure because there is no information about the resources and enemies, and the species is not well adapted to the new environment. So it means that one species that cannot reproduce again in the future can easily become extinct. And the other consequences is that because in species that are capable to reproduce more times in the future, they can skip a reproductive event. In this species, perhaps the individuals can delay reproduction to try to obtain information on the environment and learn how to better exploit the environment. And these new mechanisms are not well described by the fast-slow continuum, simply because you can reproduce many times, not only by living a longer life, but also by reproducing more frequently. And a better concept is this concept of root value, which simply describes the way the species allocate the reproductive effort in a few or in many events. So we have species with a low root value, which are the species that spread the reproductive events in many different reproductive events. And at the other extreme, we have species that allocate all the efforts in a reduced number of reproductive events. So for these species, the loss of a reproductive event can have important fitness costs. And when we compare this root value with the invasion potential of the species, we actually see a negative relationship that would be expected by the theory. So the species with a small root value also have a higher invasion potential. Of course, you see that the relationship is far from perfect, but we expect that because we know that other factors are also important to understand the invasion process of animals. And here, I show you the results of a model selection approach where I just signed the variables that are important. As you can see, habitat generalities or propagal pressure are important variables, confirming previous results. But as you can see, the root value appears as a new important variable, which is independent of other factors that has been suggested to affect invasions. And also, as you can see, there is none of the variables or life history traits related with a rapid population growth are in any of the best models. So the interesting thing is that there is no single way to be a successful invader. On one hand, you can be a successful invader because you have a long life, and this allows you to develop buffer adaptation, for example. But you can also have a lot of success in new environments if you reproduce very frequently. And this is because reproducing very frequently gives you the advantage of growing fast, but not the cost of losing a breeding event. And the fact that there are several strategies that are equally successful is maybe one of the reasons why characterizing the life history of successful invaders have been so difficult so far. And this theory allows us to understand a number of paradoxes, like, for example, the fact that very often species that are closely related tend to be very different in terms of the invasion potential. And this can be explained because the root value has low fitness, the root value has low phylogenetic effects, and the degree of phylogenetic autocorrelation is very similar to that, the one that you find for the invasion potential. And also this new theory allows you to explain the success of some groups for which we didn't have an explanation, like many doves and pigeons, the success of which could be related to the fact that they are capable to reproduce very frequently. So in conclusion, this future returns hypothesis, what it makes is integrate a number of different mechanisms that see life history as a way to deal with the uncertainties of new environments. So for one invader, not having information about the enemies or the resources, or not having had the opportunity to adapt, is very costly. But this can be solved if you have time to delay reproduction, if the cost of losing a reproductive event is low, and if you have adaptations like a large brain that allow you to learn about the enemies and resources of the environment. So that's all. Thank you very much. This is all the collaborators, and I would like to thank Montse for inviting me to give this talk. Thank you very much.